So next up we have Timo. Please.
Thank you very much. Good morning. Let me start by thanking the organizers, Jonathan, Miriam, and friends, really for keeping this conference series alive and for inviting us here. And I must say, it's really a treat for me to be back to Philadelphia and Japan after many years. And I'm very grateful to have the opportunity to report on this work on the asymptotic weak gravity conjecture and M theory with two postdocs in Hamburg, Cesar Cota, Alessandro Milino, and Max Wiesner from Harvard. And Alessandro and Max are also in the audience, and they will be ready to answer all your questions and discuss more with you if you're interested. Okay, so I think it was a good choice to start this conference with swampland ideas because, after all, the swampland conjectures are a source of profound predictions for strings and geometry in the spirit of this meeting. And in this talk, I would like to discuss this general phenomenon in the context of the Tower weak gravity conjecture, specifically the Tower weak gravity conjecture in the context of M theory. And the goal would be to show the Tower weak gravity conjecture in M theory for arbitrary Calabi-Yau threefolds, but with gauge groups that admit a weak coupling limit. So on the one hand, we'd like to be very general. So we'd like to show this conjecture for arbitrary Calabi-Yaus and a strong version of the conjecture, namely the Tower version. But this is possible at the moment in cases where the gauge groups admit at least a weak coupling limit and gives rise to the asymptotic Tower weak gravity conjecture. And I'm sure we'll have more discussions on this in the course of this week. The mathematical input, in fact, is going to be first the Kahler geometry of the Calabi-Yau threefolds, the projective special geometry of the moduli space in this case, and second, the counting of BPS numbers, which also indirectly gives us information of certain non-BPS states, as I will discuss, and these will be important, both of them, for this asymptotic Tower weak gravity conjecture. So, as you know, the weak gravity conjecture is the statement that in a quantum gravity theory with a gauge theory, and we take for simplicity only the gauge group to be abelian for the time being, and with a certain charge lattice, in such a theory, every ray in the charge lattice should support a tower of super-extremal states. So what do we mean by this? First of all, super-extremality. There are two notions of super-extremality that people refer to in the literature. Originally, super-extremality in the actual sense as being with respect to extremal black holes. So the charge to mass ratio of this tower of particles should be bigger than or equal to the charge or mass ratio of every black hole. The second type of super-extremality should really be called self-repulsiveness. This would be the idea that these particles instead should be such that the Coulomb force between two objects of that same species should be bigger than or equal the gravitational plus Yukawa force. So the two objects are self-repulsive. And this notion, this self-repulsiveness notion, was already discussed in the original paper, and Eran Paeti pointed out this important Yukawa term in the presence of Mansell scalars. So both notions of super-extremality are not equivalent in general, as discussed in great detail in this very nice work here. But at least asymptotically, for asymptotic weak coupling, they are, and therefore, whenever we look at the asymptotic weak gravity conjecture, we can, in fact, adhere to the self-repulsiveness condition, which is sometimes more tractable. What about the tower? What do we mean by the tower? By tower, we mean that along every point in this charge lattice for a certain ray, there should exist a tower of states for a multiple n of the charge, where n is in some infinite set. So not necessarily a lattice or sublattice, but for sure infinitely many for some infinite index set I. So in that sense, we want more than just a single particle to be realized with this property. So why would this be true? First of all, every BPS state is automatically extremal or super-extremal. So the existence of a tower of BPS states along a certain ray in the charge lattice is certainly sufficient for the Tower weak gravity conjecture in that direction. And indeed, a lot of efforts have been invested into studying such super-extremal BPS states. in various contexts, in type 2b, in type 2, in M theory, and we will hear more about this in this week. A challenge for the tower weak gravity conjecture arises in particular if there is no BPS tower in a certain direction in the charge lattice. And this is something which can happen often. For example, if we are in the wrong theory, there are no BPS particles to begin with. So for instance, in 4 or 6-dimensional theories with minimal supersymmetry, obviously there are no BPS particles. So the BPS particles cannot furnish that tower of super-extremal states. And in the context of F theory, this was discussed in these papers here. Interestingly, the same phenomenon also occurs in a theory that does have BPS particles, M theory compactifications to 5 dimensions with 8 supercharges. But as pointed out in this very insightful paper by Alim, Heidenreich, and Cordelius, indeed it can happen that there are no towers of states in a certain direction. And this is, in fact, the type of scenario that I'd like to understand better. And the main result of this talk is as follows. So if we look at an M theory compactification to 5 dimensions with 8 supercharges on a Calabi-Yau 3, then whenever there is a direction in the charge lattice where there's no BPS tower, and hence in particular no super-extremal BPS tower, then one of the following two can happen. Either this means that the gauge group under consideration does not admit a recoupling limit anywhere in moduli space, or it does admit such a recoupling limit. And in that case, there is a super-extremal non-BPS towers of states that replace the non-existent BPS tower, at least asymptotically. This is the statement that we are going to discuss. And this is what I would call an asymptotic version of the tower weak gravity conjecture. And once again, the point is, if there is no BPS tower, then this can be for 2 reasons, either because the theory does not admit a recoupling limit, or because there is a non-BPS tower, a non-BPS tower instead. So we are going to address this in the context of M theory to 5 dimensions. Let us briefly review the necessary geometric and physical input. Oops, this was wrong. So the gauge groups we're going to look at are the ones that come from the supergravity sector in M theory. So from expanding the M theory 3 form along 2 forms into 1 forms in 5 dimensions. So it is useful to pick a certain basis of generators of H11. One can, for example, take it to be a basis consisting of certain Kahler cone generators whose associated Kahler cone parameters we will then denote by V alpha. And given such a basis, one then, of course, expands the gauge kinetic term in 11 dimensions and finds the gauge kinetic term in 5 dimensions. So in particular, one finds the gauge kinetic matrix, which is dependent on the Kahler moduli, modulo the overall volume. The overall volume is taken to be fixed. This is a hypermultiplet. And the Kahler modulo at fixed overall volume then determine the gauge kinetic terms here. More precisely, the gauge kinetic matrix, which contains essentially the inverse of the gauge coupling squared, so to speak, is proportional to the products of volumes of devices. So this would be the volume of devices of the spaces chosen here, which sets the inverse gauge coupling squared, or more precisely, the gauge kinetic matrix in this way. Once we have this, we can then look for particles that would be super-extremal. And as I said, to the extent that we are going to look at an asymptotic version of the statement, we want to check the self-repulsiveness condition. So suppose we have in the set of charges, the set of U1s, a certain charge lattice, and we have states of certain masses whose masses are again controlled by the Kahler moduli, then we can explicitly check for the self-repulsiveness condition. There are two contributions on the right from the gravitational sector and from the Yukawa sector. The details are not yet important. All I want to show is that this is completely under control, of course, in the supergravity to analyze the repulsiveness condition once one has a candidate of towers of states to look at. Good. So let's do this now explicitly and first check for the BPS towers. So the first source for a super-extremal tower would be one consisting of the particles from BPS, the BPS particles obtained by wrapping M2 branes on holomorphic curves on the 3. And indeed, in very many cases, these towers of BPS states exist and solve the tower weak gravity conjecture for us. In fact, there is a very nice conjecture by Allen, Heidenreich, and Cordelius, who conjectured, among other things, that whenever we have a curve class on this threefold, which lies in the movable cone, then it should support a tower of BPS states, meaning that the BPS invariants or Kupa-Kumawata invariants for an infinite number of multiples of that curve class should be non-vanishing. So in that sense, we have really a tower for n in an infinite index. And recall the movable curve, the cone of movable curves, that these are just the curves which are dual, or that's just the cone dual to the cone of effective devices. And this statement has been confirmed in many examples, as we will hear more, probably in Ben's talk for sure, and maybe also in other talks. And on top of that, it also fits beautifully the physics insight that precisely for such, or not precisely, but that in particular for such states, the Black-Hole extremality condition equals the BPS condition. So these states indeed must furnish the weak gravity tower, and they do according to the conjecture and as seen in an overwhelming set of examples. So the challenge for the weak gravity conjecture in its tower version would be, what is the case if there are no such BPS towers? So in particular, when we look at a direction charge lattice that does not correspond to a curve inside the movable cone, what is the situation then? And that's what we want to address. I said already the main result that in this case, either there can be no recoupling limit for the U1s, or there does exist a super-extremal non-BPS tower. So in order to show this, therefore, our strategy has to be twofold. First of all, we have to characterize all possible recoupling limits. And this is a statement about understanding the Kahler geometry. And then check whether for all those U1s or gauge groups more generally with the recoupling limit, in cases where there are no BPS towers, there are actually non-BPS towers. So we have to understand these towers of super-extremal BPS or non-BPS states in the recoupling. So these are the two technical problems that we need to address. So let's start with the first question about the recoupling limits. Here is again the expression for our gauge kinetic matrix. The inverse gauge coupling squared, quote unquote, is proportional to products of certain divisor volumes. So it is clear that if we want to have some of the directions in the gauge group space to become weakly coupled, then some of these inverse gauge coupling squared should go to infinity. So some entries of this matrix F alpha beta must go to infinity. That's clearly a necessary condition. So the recoupling limits are certainly at infinite distance in the Kahler moduli space at fixed overall volume, as was pointed out already here. It turns out, though, that this is a necessary condition in order to really have a weakly coupled gauge group in such an infinite distance limit, once understood. We must impose a even stronger criterion. And this goes as follows. Take a particular gauge group, U1 gauge group, a certain linear combination of U1s. Then the gauge coupling associated with this gauge group is set by the inverse of this gauge kinetic matrix in this way. Since this is dimensionful, this defines a scale, which is usually called the Weak Gravity Conjecture scale in this context. And in order for the gauge group in the asymptotic limit really to become weakly coupled, we need that this scale is much below the quantum gravity scale in the limit. So that would be our sufficient criterion for the recoupling property of a gauge group, where the quantum gravity scale is the species scale that is appropriate in the limit. And thank God, in Dieter's very nice talk in the morning, we already learned a lot about the species scale, so we can build on these insights. So we need to do two things. We need to characterize the recoupling limits according to the necessary conditions, some infinite distance limits, and then we need to clarify if also the species scale condition is satisfied. And here we can build on earlier work, where the infinite distance limits in the classical Kahler moduli space of Calabi-Yau threefolds at fixed overall volume were classified. Namely, all these infinite distance limits are of one of the two types. There exists a divisor that becomes large. This can be either the base of a torus vibration, or it can be a divisor given by a large curve and a curve in a K3 or T4 fiber. So whenever we have a large distance or infinite distance limit, our Calabi-Yau threefold must admit either torus vibration or a K3 or T4, sorry, T4 surface vibration. And the limit corresponds to taking lambda to infinity, which scales the base of these two vibrations respectively to infinity and the fibers to 0. In the first case, to understand the species scale, we have to recall the physical interpretation of such an infinite distance limit. The physical interpretation is that one obtains a KK tower from M2 branes wrapping this torus infinitely many times. This is the KK tower that signals the decompactification from 5 to 6 dimensions. As we all know from the F-theory limit, this is nothing other than an F-theory limit. So the species scale in this case that we need in order to understand the recoupling limits would be the Planck scale in the higher dimensional gate group, as we learned in the first talk by Dieter. In the second case, the physical interpretation, if I may recall, is that a string becomes light, namely an M5 brane wrapping this surface fiber. It will be either a heterotic or a type 2 string, depending on whether or not we have a K3 or T4 that becomes small. And the excitations of the string now define for us the species scale. More precisely, the species scale will be given by the species scale associated with this weakly coupled heterotic or type 2 string, which to first order is set by the string scale of that object. And with this characterization in mind, we can now come to the classification of recoupling limits. They are always of the following type. So fix a certain linear combination of U1s. Let's call it U1C. We can think of this U1C as obtained by integrating the three form from M theory over a certain curve. That's really what this means. So we take the three form, integrate it over a curve, we get a one form, that's our U1C. And this curve must be one of the following two. Either the curve can be the generic fiber of a torus vibration, which in a certain limit, in the recoupling limit, goes to 0 volume, or it can be a curve inside the K3 and T4 fiber, respectively. And one has to add, this K3 and T4 fiber must not be one degenerating into various components. So in other words, in both cases, all the U1s that become weakly coupled are associated with curves which sit in the fiber at finite distance of degeneration of the fiber moduli space. So either the torus itself or a curve inside a surface fiber, which does not sit at loci at infinite distance in the moduli space of the K3 or T4, where the fiber would degenerate. That's the claim. So where does this come from? Let's look at it in a bit more detail for the torus case, the first of the two. So suppose we have a certain Calabi-Yau 3, which admits a torus vibration. And let's assume that this is the only type of vibration that we have in order to not have to consider other cases. In this case, the claim is once more, the only U1 that becomes weakly coupled is the one associated with the torus fiber itself, which sometimes we call calligraphic E for elliptic. Why would this be? Let's sharpen our intuition. We saw in the previous slides that the gauge coupling squared is proportional to the inverse squared of certain volumes, quote unquote. So the correct formula was the one that I gave before, but that's the intuition, where these volumes of devices here would be the ones dual, so to speak, to the curve. This is not a well-defined statement, but we know what we mean. In the present case, we have of such an infinite distance limit, the curves that shrink to 0 are the torus fiber itself. And the dual divisor, so to speak, is the basis. So the gauge coupling squared scales like 1 over lambda squared, lambda to infinity in this type of infinite distance limit. So it goes to 0. So it certainly becomes weakly coupled necessary. That satisfies the necessary condition. What about the sufficient condition? We have to now compare this to the species scale associated with this limit. This is the species scale for the decompactification from 5 to 6 dimensions in this F-theory limit. The relation between the species scale and the KK scale for such decompactifications is given here. We also saw it today in Dieter's talk in a version. So the species scale at the end of the day is related to this scaling parameter in this fashion if you plug in all expressions. And you can see that indeed the gauge coupling squared with respect to the species scale squared goes to 0. So this is really a weak coupling limit. I'm stressing this because one could think that there could be more curves that are associated with the recoupling limit. For example, there could be curves in the non-generic fibers of our torus vibration. They will also satisfy the necessary condition that the gauge coupling times m Planck cube goes to 0. In this case, it turns out the scaling is milder due to certain cancellations. But compared now with the species scale, we see that this gauge coupling squared does not go to 0. Hence, these extra U1s that are associated with the extra curves in the fiber, and these are precisely the fibers at infinite distance in the fiber moduli space, hence the criterion, that these U1s do not become actually weakly coupled. Okay, so this is very simple. There's only one type of such U1s that become weakly coupled. So our job is very simple. Is there a tower in this direction? And the answer is clearly yes. There is a tower, in fact, of BPS states charged under this extra U1 because we can take M2 branes wrapped arbitrary number of times on the torus fiber. The Gopa-Kummer buffer invariants at genus 0 are just given by the Euler characteristic. Even if the Euler characteristic 0, the individual BPS states are non-zero. This would just be a sign of cancellation. So we for sure have a super-extremal BPS tower that satisfies the asymptotic weak gravity conjecture in this case. And the interpretation of these states is, of course, as the KK tower. Along all the other curves, in particular in the fiber, we in fact do not have BPS towers. This is an example of curves where no BPS tower exists. You can wrap an M2 brane once on such one of these green curves, but not several times. So there is no tower. But we are not sad about this because this tower is not called for, at least by the asymptotic version of the weak gravity conjecture, because the U1 can never become weakly coupled. And put differently, these U1s which do not have a tower and which do not become weakly coupled just become gauge groups in the 6-dimensional F-theory limit where they are not weakly coupled. And these are precisely then the ones, if the Calabi-Yau 3 doesn't exhibit other vibrations, which also from the 6-dimensional F-theory point of view can't become weakly coupled, and for which there are no BPS towers. No BPS towers. And in fact, no towers known. Okay, so this was the first of the two cases. Now let's come to the more interesting one, where we are looking at limits in which a K3 or T4 fiber volume goes to 0, and I'm only going to discuss the K3 fiber in this talk. In this case, the only U1 which can become asymptotically weakly coupled is one that is associated with a curve that sits in a generic fiber or in a fiber that degenerates at finite distance in moduli space, so it doesn't split into several components. Again, one can go through a similar analysis. First, compute the gauge coupling squared. I'm not showing the details. And then compare this to the species scale associated with this limit. The species scale here is set by the tension of the emergent heterotic string. And as we learned in the morning, the species scale, therefore, is associated to the string scale. In fact, as discussed in these two papers, there are log corrections. So we see that the gauge coupling squared with respect to the species scale squared still goes to 0, but only log suppressed. But it satisfies the criterion that we have a recoupling. So we therefore now have to answer the question if there exists a tower of BPS or non-BPS states with respect to such curves which sit in generic or at finite distance degenerating K3 safe fibers. And this is a question that, of course, has been tackled many times in the literature and goes back a long time. In particular, in order to address this question, we have to recall that these curves in the K3 fiber, I'm discussing the K3 case here, sit in a lattice which can be decomposed into a self-dual and anti-self-dual sublattice of a certain signature. And we have to distinguish now between the curves whose self-intersection is non-negative and those whose self-intersection is negative. If the self-intersection is non-negative, in particular when they are in the self-dual part, in particular, then a BPS tower for sure exists. First of all, this is an agreement with the conjecture that everything that is in the movable cone should admit such towers, and such curves are in the movable cone. They are deformable and in the movable cone of the fiber, and the fiber is movable over the base, so everything is movable. In addition, this is actually a theorem, not only a conjecture. This is an agreement with the well-known BPS counting of such curves inside such K3 fibers, goes back various decades to famous work by Harvey and Moore that computed the Gopa-Kummer buffer invariants as coefficients of certain modular forms. And we see here that these coefficients are non-zero whenever we have in its argument a non-negative number. Hence, whenever we have a curve of non-negative self-intersection, any multiple of this curve will also have a non-vanishing BPS number. And these are precisely the non-contractible curves inside the K3. So we have a BPS tower. What about now the remaining curves? And this is the most interesting part. In this case, no BPS tower exists. The curves are rigid in the K3 fiber, not movable, so we do not expect a K3. We do not expect a tower. But nonetheless, the U1 is weakly coupled. So what's going on? The claim is that instead there's a tower of non-BPS states that takes the role of the weak gravity conjecture particles. And these states are a special subset of the set of excitations of the MSW string obtained by wrapping an M5 brane on the K3 fiber. This is just the emergent heterotic string. A certain subset of these states, in fact, is precisely the furnishes the set of super-extremal non-BPS towers. To see this very briefly, we have to use, or we can use, for example, this would be one way of seeing it, by using results from BPS counting, in fact, in 4 dimensions. This makes use of the duality between M theory on the Calabi-Yau threefold times a circle and type 2A string theory on the Calabi-Yau 3. Let's take the following dictionary, more under consideration, namely, let's consider a bound state of an M5 brane on this K3. This gives the heterotic string with a certain winding number and KK number along this extra S1, bound to an M2 brane on some curve on this K3 fiber. This gives rise to a certain set of BPS states in 4 dimensions, and these BPS states are D4, D2, D0 bound states of a certain D4, D2, and D0 charge vector. And the point is that these BPS states can be viewed as winding and KK modes of this heterotic string obtained from the M5 brane on the K3 at KK level n. And in the special case where the winding number is 1, we can use the trick that the level matching condition, the KK number and the left moving excitation number appear at the same footing, only true for winding equal 1. So rather than thinking of these as states with winding number, with KK number n and states in 4 dimensions, we can replace the winding number by the left moving excitation level. So we interpret these as excitations of the heterotic string in 5 dimensions, not in 4 dimensions. We then have to do level matching for the right moving states. This gives therefore rise to non-BPS rather than BPS states. So in that sense, the information about the 4D BPS states of a certain charge vector carries information also about non-BPS states in 5 dimensions, where the left moving excitation number is taken from the KK number in this D4, D2, D0 bound state. So what we need to show is if a certain set of super-extremal states exists, and for this we can do use the state counting from type 2A, and as it turns out, the states at KK or left moving number, depending on how you want to interpret it, and given by -1/2 Q squared, where Q squared is the intersection of the curve in the fiber, those states turn out to be super-extreme. So we need to show that these states are always there, such a tower always is there, and then check super-extremality. Showing that the states is there makes use of general properties of the BPS partition functions in 4 dimensions. These Donaldson-Thomas invariants have been discussed at great detail in the literature. And in fact, using non-trivial results about the state counting, one can indeed show that the states in questions are present. I'm not going to go through this now in the talk. Having established the existence of these states, what remains is to check that they are actually super-extremal. And by super-extremal, we now mean super self-repulsive in the limit, at least. So we take those states and we have to explicitly check if this equation, the self-repulsiveness equation, is satisfied. And this, of course, can be done. We use the mass squared for these non-BPS states, at least at recoupling asymptotically. This should be given by the classical result. So it's related to the tension of the string. But since we're in 5 dimensions, there's in fact also an important contribution from the Coulomb branch in 5 dimensions. And we compare this to the gravitational and the Yukawa force on the right-hand side. And one sees that precisely in the limit, one finds a massive cancellation between both sides, and one precisely finds that these states are marginally super extreme. So and this makes use precisely of this property, n equal minus 1/2 q squared, the special set of states whose existence one could show in full generality. So in that sense, we have a non-BPS tower. Let me conclude. I've argued that the asymptotic tau weak gravity conjecture in 5 dimensions is satisfied because whenever there is not a tower of BPS states that would play the role of the weak gravity particle, we have a non-BPS tower, at least in all those cases where a weak coupling limit can be identified. And this is, in fact, a 5D version of a statement that can similarly be drawn in 6 dimensions or 4 dimensions with n equal 1 supersymmetry, as was discussed in the F-theory paper. There are lots of technical questions left. I didn't discuss much, or in this case, in this talk at least, not at all, the situation where we have a T4 vibration rather than a K3 vibration, and how to identify the states in this case. But what I find more pressing are the conceptual questions, namely how to interpret this. What now if we do not have a tower in a certain direction, neither BPS nor non-BPS? Well, from this result here, one thing we know that in this case, the U1 in question is always strongly coupled. We can never take a parametric recoupling limit. So if the tower, the putative tower, sits at the weak gravity conjecture scale, which would be the natural assumption, then it would always be at or above the quantum gravity scale. So one might debate now if it makes sense to consider such towers, in particular when they are non-BPS, because this is the case where a problem arises. And yeah, I'm sure we will have more discussions on this. One could take the point of view that only the asymptotic version makes sense, or at least has to be satisfied, but this is now a matter of redefining what your conjecture is. At least this is the situation as far as the facts are concerned. Okay, so we are enjoying and looking forward to a week of talks in this wonderful venue. And it's too early to look into the past, but it's nonetheless good to be prepared. The conference series Strings and Geometry will go on, and next year we look very much forward to welcoming you all in Hamburg. This is a typical Hamburg evening in March, early March. Those of you who have been to Hamburg know that it's in the subtropical climate zone, so it will for sure be sunny and warm, and I look very much forward to welcoming you next year. Thank you.
Very interesting question. Very nice. In a case where there is no directional recoupling limit, so we cannot ask about the power version of recoupling, we can ask about the regular version.
Yes.
Do you have any evidence that that is satisfied or not?
The regular version, I think, is satisfied. This will be the context in particular, for sure, of I think of Ben's talk. I'm not contesting the regular version at all. It's more about the tower.
The other question I have is we get comments about it sounds mysterious that the BPS quantity has information about the non-BPS matters, but is it like it just so if you take elliptic genus,
Exactly.
It captures the non-BPS side, like the rise of partition. You know the non-BPS to that direction. Are these the fiber versions?
Yes, absolutely. And if I had time to go through the argument, this is precisely how it goes. One looks at the elliptic genus from 5 to 4 now, and then relates this to the BPS states and does exactly what you want.
Yeah, so I have a question. So if we were to have the power of states, or even when you have I think there's a non-BPS tower states, the tower doesn't extend even far, the third they have a lifetime, and you start with decay. And the limit in the small couple limit maybe what happens is that they have already decays.
Yes.
Could you get a picture like that, try to understand what is the lifetime of different states, and maybe interpolate the one image from another from the old there and to the some exploding?
Very good question. Yes, one should do that. In fact, even more harmless things start to happen, namely the self-repulsiveness condition gets modified. So this was I showed the asymptotic version. As soon as we go back into the moduli space, both sides will be corrected of that equation. So first of all, one has to check if one can match this to known corrections to masses of these strings. This is already a non-trivial question. And then what happens to the states as far as their lifetime is concerned? So the logic here is, if we have at least a limit at infinite distance, then I would believe that there could be some trace of non-BPS states by first going to the limit and then hoping that everything goes well. It's a leap of hope, but at least one can take a limit to start with. In the cases where we don't have the limit, I don't even know what to do. So that's why I'm not sure what to think about the tower version, not the usual version for those cases.
Yeah. We talked about the non-existence of the BPS tower in some cases. You said there are definitely BPS towers outside of the cases.
Yes.
It's not there. It doesn't have to be.
There can certainly be, as you know very well, BPS towers outside the movable cone. It doesn't have, in those cases, it could be that they would not have to be there from the asymptotic point of view. In some cases, we know that there's no tower. So for instance, I mean, the conifold case that you discussed, there, you know, there's no tower. This case here, hang on. This case here, that's another example. We know that there's no tower, no BPS tower, and also no non-BPS tower, because we can't, and we do, so we know there's no BPS tower, this is known, and we do not know of a non-BPS tower. Not in this work. We thought about the corrections in the 4D n=1 context with Clever and also with Max in previous papers. And so we imposed the weak gravity conjecture for those states, and from that made a prediction for how the masses would have to be loop corrected, which is of course something that should be counter-checked against a proper loop correction in string theory, which hasn't been done yet. I think there's a lot that one could look at there. The -1, you mean the -1 from the vacuum energy? Or? Yes. Oh, that is fine. Yeah, the -1 is fine. That makes it slightly super extreme as opposed to. Well, no, I think one does have to worry about the correction. So there are cases where we can take alpha prime corrections into account, and they become important. So they do correct both sides.
Let's ask one question when we talk about it. Yes.
Another question by Elon. If I actually say again, what is a concrete example of an infinite distance limit in which you don't satisfy the condition in the super scale? So that all states are about the super scale, and it's not clear.
Okay, thank you. Here, for example, here I take an infinite distance limit, the torus fiber small, and we have curves that would define a U1, say. This U1 would have this gauge coupling squared, but the species scale is at the same scale. So this does not become weakly coupled. And this is, of course, known because they just become the U1s in F theory, where they are not weakly coupled.
Okay. Thank you.
Thank you.